Hi, my name is Genevieve Bouchard. Welcome back to Vehicle Dynamics series. Now that we saw the basic of suspension at the last episode, let's now more go in depth on some components like springs and dampers, because today we're going to talk about ride dynamics. I'm here with Ariel and Vincent, and they're going to help us understand all those concepts. Hi, Vincent. How are you doing?
Hi, I'm doing pretty good.
What about you, Ariel?
Pretty good.
Cool. So, what are we going to talk about exactly today? We're going to do a review of goal of suspension as we a little bit saw last time. We're going to talk about why we use spring and dampers, so the role of them. We're going to see sprung versus unsprung mass, stiff versus soft suspension. We're going to see the types of spring and the spring selection. And finally, we're going to go over some damper theory. So let's start with the basics of suspension.
Yeah, so we'll do a quick review on this. So the first part of it is that we need to know that the suspension has multiple roles in a car. So the first one being that we need to keep the wheels planted to the road and have the largest patch of tire always in contact with it. So that's where the suspension will help. Another goal of the suspension is to keep the car as stable as possible. So more exactly, like especially in cars that are low, you don't want them to hit the floor or like go side to side all the time. You also don't want the tires to roll off of their optimal angle. Otherwise, another well-known rule of the suspension is to absorb the imperfection on the roads. So like bumps or holes, that's where the suspension comes into play. Otherwise, suspension will also be used to transfer the weight of the car equally amongst the wheels. So like, let's say when you turn or brake, you don't want a specific wheel to get more force or weight than another one. Finally, in cars where the aerodynamic performance is highly studied, like for example, the Formula One car or our own Formula Electric car, you don't want the car to move around every time you do anything. You want everything to stay in the same place as you designed it. So that's where the suspension will help.
So now, why do we use spring and dampers?
We use them because, well, first of all, if we don't have any suspension or anything to absorb the bumps, all the force from the road will go straight into the chassis. So that's where we'll see the car jumping around and not being in contact with the road, which is what we want. And then if we use only a spring setup, it will absorb the energy from the road. However, it will also immediately release that energy back. So you'll see the car bounce around similarly to what a suspension will have in the end. So that's where the solution of the damper and spring setup came about. So the damper is used to reduce or absorb the energy from the spring and transfer it as heat instead of kinetic energy.
Good. Now, can we know more about what is sprung mass and unsprung mass?
Yeah, for sure. So the suspension controls the sprung and unsprung weight of the car. So the difference between this is that the sprung weight is the weight that is supported by the suspension. So for example, we have the chassis, the engine, the driver, the gearbox. So anything above the suspension. So unsprung weight on the other end is any weight that is not supported by the suspension. So in terms, this includes the wheels, the tires, the brakes, or anything that is below the suspension. Obviously, the suspension has a certain weight and as such will count as either sprung or unsprung mass. Usually, we estimate that about 50% of the suspension weight will be counted as sprung mass and the other half as unsprung mass.
Now, can you talk a little bit about the types of movement to be controlled?
Yeah, of course. So, like I said before, one goal of the suspension is actually to control how the car will move when we do different things, such as braking or turning. So the different kinds of movements, there's a heave. So heave is when both sides of the suspension will do the same stretching or compression. So let's say we take a bump equally on the right and left side of the car and the whole car lifts, that is heave. There is also roll to consider. So this is when you corner, the car will tend to lean on one side. This is due to when we corner, the weight of the car transfers to the outside of the car. And as such, the outside wheels will compress and the inside will stretch. There's also a yaw, which cause understeer. So this is when the car turns less than what you are inputting. And there's oversteer, which is the opposite, or when the car turns more than what you actually want it to turn. Finally, there's also the pitch rate to control. This is when you brake, so that will be dive. So the car will lean forward. And there's also squat, which is the opposite. So when you accelerate, the car will tend to lean backwards. So these movements, we have to manage them, to find a way to manage them. So heave, for example, will use heave springs. So there's actually the left picture here that shows one example of heave spring. So it's a spring that connects both sides of the suspension and only will act when both sides are stretched or compressed equally. When cornering, this will not affect anything. Roll, on the other hand, is controlled with anti-roll bars, which is like a torsion spring. You can see it on the right picture that links both sides of the suspension. So when one side compresses, it tries to compress the other side as well, so limiting the roll during corners. However, it's important to consider that since we compress both sides at the same time, it can lower the car during turns. So this is to be considered when you set up the car.
Can you more talk about stiff versus soft suspensions now?
Yeah, for sure. So we'll go very basic here, but usually a stiff suspension will generally be a bit more bumpy since it doesn't absorb the road imperfection as well as a soft suspension. However, the car will remain more stable. It will not move around as much as a soft suspension, which makes it more responsive during turns and more stable aerodynamic grip, since the car doesn't move around, as I said prior. A softer suspension, on the other hand, will absorb the imperfection of the road. So if you have a very bumpy road, you'll tend to want to go for a softer setup. However, it will cause more movement of the chassis and as such less aerodynamic performance, and it will also be less responsive in turns. So we need to find a balancing act for every track to fine tune everything to extract the most performance. It's not like you go either stiff or soft. You need to find the balance.
Exactly. Okay. Let's now more talk about the types of spring and geometry.
Yeah, for sure. So there's many designs of springs that are used for many different applications. So here's a few examples. There's the leaf spring, which we can see on the left image. This type of springs are pretty cheap and strong, which is why you'll usually find them in pickups or trucks. There's the coil spring, which is probably the most common type of suspension you'll find in road cars today. They can be described as a metal bar wrapped around an axis. So that's what you can see on the right picture here. They're available in many different forms, many different setups. So for example, you can have springs with linear compression rates and other with variable spring rates. So I'll talk about this a bit more later, but that's an important thing to consider. And finally, there's the torsion bar. These types of springs are usually used in like Formula type car. For example, Formula One, that's the best example we can have. So they're used because they're very compact, very lightweight, and they're very simple too. It's basically just a single bar that has one end fixed and the other is free to rotate. So basically what happens is when we rotate, it creates like a spring effect. So that's how it works. The complex part about the suspension, however, is that they cannot work with linear movement, which is usually what happens when you take a bump. So you need to use a push or pull rod setup to actually make it work. So just like different types of springs, there are many types of geometry of suspension that can be used. So there's the single arm geometry, which is found in, I'd say, most cars, road-going cars. They're pretty simple and they're cheap to produce. But there's also the double arms setup. So like the image here is a perfect example of a double arm setup. But even in double arm setups, there's a wide variety of geometries that can be used. So there's, for example, the double transverse, which is what Formula One car uses, but there's also the double trailing arm. It's a suspension that exists.
Okay, let's more talk about springs now.
An important thing to note before going into more details about spring is that springs can be used in conjunction with other springs to create a suspension with hybrid characteristics. One important characteristic to note is the spring rate. So every spring will have its own unique spring rate, so it's very important to select it accordingly. A spring rate can be best defined as the amount of force that the spring will deliver depending on its level of compression or torsion. So in coil spring, the rate will be determined by the thickness of the coil and the number of coils present. In a multi-spring setup, the main spring will have either a linear spring rate or a progressive spring rate. So the linear spring rate means that whatever the compression is, the spring rate is the same. The progressive spring rate, on the other hand, will change depending on the level of compression. The tender spring is a spring that is used to create like a softer start of the suspension and then a stiffer suspension. So the tender spring is usually softer, than the main spring, and will be put in line. So this is a perfect example here on the right of a main spring with a tender spring here to make it a bit softer in the beginning. We can also have a helper spring, but this does not affect the way the spring rate will evolve during a corner. And depending on how the springs are fitted together, so whether it's in line or in parallel, it will affect differently how the spring rate will be affected. Torsion bars, on the other hand, will have a linear spring rate all the time. Another key aspect of springs is the concept of preload. So preload is an important ride dynamics tool, as it allows us to like fine tune how the suspension will react in corners. So first, what is preload? Preload is a compression or torsion that is manually applied on the spring. This means that even at rest, there will be a load applied on the suspension. We use this because it can increase the ride height of the car, and also because it can reduce the travel of the wheels. This is due because the suspension will not start to move until the preload is surpassed. So let's say you put a 200 Newton load in your suspension, you won't see any movement until there is more than 200 Newton of force applied to the suspension. On that note, running more than 100% preload is a very powerful tuning tool. More precisely, running 100% preload means that your preload that you apply will be greater than the maximal corner weight of the car. So whenever you turn, the car won't change its right eye. It won't compress. This makes the car very reactive in the turns, and means that it won't move until the downforce breaks this preload. Furthermore, this preload can be combined with bump rubbers, which are these rubber parts that are used to prevent the suspension from hitting itself when it's very compressed. So with this, we can effectively run three different spring stiffness. So there will be the preload, which will make the car reactive in low-speed corners. Then once we break the preload in mid-speed corners, we'll have the compliance of our mainspring that we selected. And then once we are in a high-speed corners where there will be a lot of downforce, we'll be using the spring rate of the bump rubbers. So that is a very powerful tool to tune the car.
So how do you select spring rates for your car?
Yeah, so like I said earlier, each spring will have its own spring rate. It's a unique thing. So you need to make sure that when you select one spring, it will work with how the car is designed. You don't want to have a spring that works against you. So the first step in selecting the right spring rate is to find the right frequency, or more accurately, the natural undamped frequency of the car when it's in use. This frequency can be different between the front and rear, so you have to consider this. Usually, you'd get about a 10 to 20% difference between the front and the rear. And there's two main philosophies when selecting this frequency. The main one is to have a higher frequency in the rear, since the front of the car will take the bump first. So if you look at the picture in the bottom right here, as you can see, the front of the car takes the bump first, and then the rear takes it. So you want the rear to be able to catch up with the front to make them synchronize. So that's why you'd want a higher frequency in the rear. However, there's this other theory that says that you want a higher frequency in the front to get a faster response when entering corners and a faster acceleration at the end of at the exit of the corners. Usually, a good idea of ride frequency would be 3 to 5 hertz for high downforce from the cars, like we're building. But it can be lower than this. So for example, for moderate downforce cars, it will be more about 1.5 to 2 hertz.
Yeah, so here at MFA, we really aim to be between 3 and 5.
Exactly, yeah.
Mm-hmm.
Then the next step of finding the spring rate will be to find the motion ratio of the car, which is directly influenced by the suspension geometry. So if you want to know how to find it, it's basically you jack up the car and then measure the difference between the height between the top and the bottom of the suspension, and also the difference in height between the wheel and what it was before. And then you do a ratio of this, and that's your motion ratio. Finally, you find the spring ratio, which can be found using the formula right here.
Okay, so to find the spring ratio, you need to have the spring rate. To find the spring ratio, you need to have the right frequency, the sprung mass, and the motion ratio of your car. So the motion ratio is an important concept. So I just wanted to make sure I understand it properly. So you need to measure the change in height of the wheel and the change in length of the spring. So how the spring reacts, like how much the spring reacts when the wheel height change.
Exactly, yeah.
Yeah, cool. Okay, so now Ariel, are you still with us?
Yes, I am.
Cool. So you can now talk about dampers. The dampers are the shock absorbers. It's the same thing.
Yes. Cool, thank you. So yeah, as Vincent mentioned at the beginning of this presentation, dampers are very important in the car suspension system. And we combine them with the springs, of course. So basically, also as previously mentioned, when a spring in the car suspension is compressed, it stores a large amount of kinetic energy, and this is released when the spring extends. So what dampers do is that they convert this kinetic energy from the spring into heat energy, which is much more easy to dissipate. And without dampers, basically the spring would oscillate at the natural frequency of the unsprung mass. So as this picture shows, with the damper, what happens is that the oscillations slowly decay. So that's why dampers are so important. Yeah, so now for just how dampers are made. So basically, one end of the damper is connected to the chassis, and the other end, with the use of a linkage or directly, is going to be connected to the suspension. And a typical hydraulic damper, which is what we use in our cars at MFE, consists of a piston which moves in an oil-filled cylinder, and that's what we have here in the image on the right. And what happens is that when relative motion takes place between the sprung and unsprung mass, the dampers move up and down, which moves the piston in the oil-filled cylinder. And the piston forces the oil through a series of holes. They're a bit hard to see, but there's like holes in the damper. And by forcing the oil through these holes, the kinetic energy is being turned into thermal energy. And this whole process stops the kinetic energy from being transmitted onto the chassis. And also another important thing with damper construction is that the size of these holes, which the oil goes through, determines the softness of the damper and the system's movement speed. So now we're going to talk about the three main relationships of shock absorbers. And the relationship we're talking about is between piston velocity and resultant damping force. And this is also known as the characteristic of the shock absorber. So this relationship can be linear, where you have an increase in piston velocity leading to an increase at the same rate in damping force. Or the relationship can also be progressive, where the damping force will increase at a greater rate than the piston velocity. Or finally, you could have a digressive relationship, where the damping force will increase at a lesser rate than the piston velocity. And there's an image there showing, I guess, force measured against piston velocity.
Can you now talk about the damping ratio, Ariel?
Yeah, so the damping ratio is an important concept. It's essentially a unitless normalized value, and it summarizes the damp response of a second order system, which is what the spring damper system is. And basically, it is calculated using the damping coefficient, which divided by the critical damping coefficient. and the critical damping coefficient is based on our system's natural frequency. So if this ratio is greater than 1, then we say that our system is overdamped and it returns to equilibrium without passing it or overshooting it. So you're not going to see any oscillations in the springs. And if a ratio of 1, a damping ratio of 1 means that the system is critically damped, and this means that it returns to equilibrium, but this happens more quickly than in the overdamped case. So you can see in the image how the overdamped curve is going to take longer to reach that equilibrium position. And the ratio of less than 1 is underdamped, which means that the system returns to equilibrium, but only after it exhibits some oscillations. And the lesser the ratio is below 1, the more that the system is going to oscillate before returning to equilibrium. But for our car at MFE, we have our dampers have a ratio of about 0.7, which is underdamped.
They don't necessarily have it, but that's the ideal that we want to have. Yeah, exactly. But why are we talking about damping ratio right now? Like, why am I learning about damping ratio?
Well, it's an important value for so that we can make sure that we choose a suitable damper and that we make sure that our damper setting is correct. Because we, in the end, at MFE, we buy our dampers and we want to make sure that the dampers have the right damping ratio for the kinds of racing that we're going to be doing.
Perfect.
Great. So now we're just going to talk about a few other things to consider for dampers. So it's very important that the shock absorber or damper is installed properly with the proper length, because it can actually limit the bump or droop travel of the suspension. So if it's not installed properly, so we got to be careful with that. And if, for example, there's a droop limit due to a shock with not enough extended length, what can happen is that a wheel can be pulled off the road surface by the damper at some point when there's a lateral load transfer. And this is not something we want, obviously. And another important thing to watch out for is the amount of displacement the shock gets for a specific amount of wheel travel. And the more we have of this, the better that the shock will dampen. And finally, it's very important that we've got cooling in our dampers, because when converting the kinetic energy into thermal energy, in the process described earlier, the damping fluid becomes less viscous and gains bubbles. And these bubbles can cause an inconsistency in the damping and the handling because they reduce the damping force. So we don't want to have those bubbles. And there's a picture of bubbles there in case that's...
In case you didn't know what a bubble was.
That's enlightening for you.
Okay. So thank you guys for this presentation. We learned about ride dynamics, about springs, about dampers. And if you guys want to learn more about cars and different subsystems of the cars, I really encourage you to read Tune to Win, Suspension, Geometry and Computation, and Fundamentals of Motorsport Engineering. So thank you, Vincent. Thank you, Ariel. And I see you guys in the next episode.